Welcome back to Generative AI and the Delivery of Legal Services. Today, we're going to learn about how generative AI works. First, we'll learn about AI concepts and relationships. Second, neural networks and deep learning, followed by how ChatGPT works, and finally, the race to general intelligence. Let's look at some basic AI concepts. First, artificial intelligence. It is the use of a computer to mimic human intelligence. Machine learning is a subset that focuses primarily on using algorithms and statistical methods to help a computer learn. Deep learning is a particular method that uses neural networks to aid a computer in learning from data. And finally, transformers is another technique that uses attention, and we'll go into that a little bit later, to be able to understand relationships between words. And within machine learning, there's different types of machine learning. There's supervised learning, where humans label data so that a computer can classify different types of data. Unsupervised learning is actually where there is no human in the loop. There is no human labeling. The computer actually clusters data and categorizes it based upon that. Finally, reinforcement learning is where you provide a reward incentive to the computer and then reward it when it gets things right. So neural networks and deep learning, they form the basis of how this technology works and why it's intelligent. So let's look into that a little bit. So neural networks, obviously it has neural or neuron in the name because it was inspired by the human brain and the neural structure of a neuron, which, as we may have learned in biology, has dendrites to take in nerve impulses and then processes it and sends it out through axons to other neurons. In a similar way, the perceptron is the digital equivalent that was inspired by the neuron. And so on the left-hand side, you can see input 1, input 2, to input n, meaning just carrying that forward to 3, 4, 5, 6, and so on. So you have multiple inputs. Those inputs are modified by a weight. A weight is a relationship between these different inputs, and then those are processed in this central circle that you see here with an F on it, which is a function, an activation function, that further modifies the input. There's also another aspect called a bias, which is a constant. It is a number that's added to the weight and the input. So essentially all of this together acts as a function to transform the input in some way. And as we'll see, that happens kind of behind the scenes within this function in the middle. And this is one of the reasons why people refer to it as a black box, because it isn't entirely clear how those calculations take place when we have much more complex structures. Suffice it to say, the inputs are modified by the weights and biases and the activation function, and then on the output here, it produces some output that could be a prediction, for example. And so let's go through how it learns. Let's break it down. Remember, an algorithm is a recipe, and here we have a recipe for helping a computer to learn. Number 1, it receives an input of some kind, like a sentence. Second, it makes a prediction. What would the next word in that sentence be? Third, it checks how close that prediction was to a correct outcome. So it likely has an example of a correct outcome. And then finally, it adjusts the weights and biases that I mentioned, those modifiers of the input, so that the next time it gets a better prediction, gets closer to being correct. And it's rinse and repeat. As you see with the arrow, it just continues to get better and better. And so here's a graphic to illustrate that. You have these multiple inputs coming in, being modified by weights. And just think of the weights as little dials where you can dial in the accuracy of how the input is affecting the output. Is it getting close to what you want in the output? If not, you can see that when it comes through and creates the output, if there's an error, it goes back and it modifies these weights, the dials, to make the prediction and the output more accurate. And so that method of taking the input, modifying it, creating an output, and then calculating the error, or the loss is how it's referred to in AI, taking the error and then back propagating it, sending it back. So the technical term for sending it back to make it better is back propagation, and modifying the weights, and so on. That's essentially how a neural network learns. And so if you multiply this, you add on layers of neural networks on top of each other. And that's where deep learning, that's where that moniker comes from, because you have several layers deep of these neurons inputting and outputting to each other. So the layer on the far left is the input layer, on the far right is the output layer, and then in between, it could be 3, it could be 5, it could be hundreds, if not thousands of layers deep. We refer to that as the hidden layer. And so that is where the black box comes from, that idea, because it's not exactly clear what's happening in the hidden layer. We do know that the weights and biases are being modified to come up with more accurate predictions, but it is very, very complex. And it's so complex that a model like GPT-3 essentially has 175 billion parameters. Parameters is the weights and biases, those little dials that make the prediction more accurate. So GPT-3 had 175 billion of those dials. GPT-4, by comparison, we believe, because it hasn't been released publicly, but the estimate is about 1.76 trillion little dials, or weights and biases, to parameters to make it more accurate. And so, kind of like a drawing, you have a rough sketch at first that becomes finer and finer detail as you put more marks on it and make it, you know, much more exact. And that's kind of the idea with adding more and more dials. It's almost like the resolution on a TV. The smaller the pixels are, the more accurate and detailed the picture can be. And so I had mentioned a transformer. This is actually what a transformer looks like. This is an outline of the technology and how it all maps together. You don't have to learn this. I just put it here because you should know what it looks like and you can refer back to it. But it does allow the computer to understand the relationships between different words, going backwards and forwards. And so to understand that in a more concrete way, let's look at this. So the artist painted the model with a brush. So here, we as human beings that have learned English understand that with a brush modifies how the artist painted, right? But in this other sentence, the artist painted the model with long hair. This prepositional phrase modifies the model. But we only know this because we have made it common sense to look back and forth to understand the relationship between different words. We're not just reading it going forward. Because if we read these sentences just going forward, we might make the mistake in associating, let's say, long hair with painted rather than the model. And so that kind of understanding of relationships between words is called attention. And that is the new innovation that transformers brought to the table, is to be able to understand these complex relationships going backwards and forwards between words and sentences. So with that, let's take a look at how ChatGPT works. How does it put this together? Well, first you might ask a question like, what sound does a cow make? Now, what's happening behind the scenes is that's taken as a request by OpenAI. And it looks something like this. The request is sent to this particular URL, which is an API for completing the request. And of course, you include an API key, which is kind of like a key to get in the door behind OpenAI to access their model. We want to use GPT-4o. The prompt that goes through the question is, what sound does a cow make? The response could be up to 500 tokens. And the temperature, which is, it's a dial where you could set how creative the model could be or how random the answer could be, we'll set to 0 so that it's factual. And then we get back a response, a cow goes moo. So it comes up with a cow goes moo by referring to its training data and estimating what the closest word is that would be responsive to your request. So naturally, what sound does a cow make? Cow goes moo. But how does it actually work? The way we get words into AI is by changing it from a word to a number, because computers work best with numbers, right? So we take cow, we run it through what's called an embedding model to create an embedding. An embedding is just a collection of numbers. And in this case, we're using a model called Text Embedding ADA 002, which is a model OpenAI provides to create numeric representations of words. And it has 1,536 dimensions, or 1,536 numbers that represent a particular word or sentence or paragraph. And that can sound a little scary, I understand, because 1,536 dimensions, we start thinking about space and like, how could you possibly have 1,500 plus dimensions? One way I would suggest to think of it that makes it a little more easy to wrap our heads around is just think of it as descriptors or like adjectives. If you're going to describe a friend of yours, you might relate, what their height is, their eye color, hair color, age, what kind of clothes they wear, what kind of music they're into, right? So you can go on and on and on with all of these adjectives to describe someone. And you can think of those as dimensions that describe that person. The more dimensions you provide to identify who that person is, the more likely you'll be able to find them or relate to someone else about who they are, and then they'll be able to identify them. So in a similar way, all these dimensions go towards better identifying cow in relationship to other words. And for fun, I actually generated the embedding for the word cow through the ADA model. And these are all 1,536 vector representations of cow. And you don't need to know this, but I just wanted to show you that this is the extent of description of cow in numbers. So to look at this spatially, to make sense of it, these different dimensions can be plotted in some space. Let's look at it as 3 dimensions, as we're showing here. You might have cow here in the upper left-hand corner, and so naturally, when you're using numbers to plot it, there would be other words, and these other words would be in nearby spaces if they had a similar meaning. So here, cow is next to moo. It's also near cowboy. On the other hand, cat is close to feline and close to meow. So that's why when you ask an AI, what sound does a cow make, it looks towards the nearest neighbors for having an understanding of what that might be, and then using the intelligence that it has to infer what would be the correct response. So let's talk now about the race to general intelligence. This is something that's ongoing, it's currently happening, and there's seemingly a new model coming out every week. So let's understand what general intelligence is. And the way to do that is to contrast it with narrow AI. So narrow AI, as we discussed in the first module, has to do with doing one particular thing really well, like chess, or playing Go, or voice recognition, but these narrow bands of skill. General AI is a method that unifies all of these together, that just like we can as humans generalize what we learn to maybe apply it across disciplines, the AI, when it achieves general intelligence, would be able to apply learnings across different disciplines and also learn new ones. There's different terminology that's been used over time for this. Probably the first is von Neumann and Ray Kurzweil, the singularity, which is this point in time when human intelligence is matched and then exceeded. Also referred to as artificial general intelligence, which is the moniker that most people use right now. Superintelligence by Nick Bostrom 10 years ago. And powerful AI by Dario Amodei, who's the founder of Anthropic. He doesn't like using, superintelligence or the singularity because he believes it's all on a spectrum and AI will become more and more powerful, but that it doesn't make sense to focus with dramatic pause on the singularity. So how is this happening? Well, it's been determined that the more computing power that you add along with data creates more and more intelligence. You'll see here on the left, you see where it says test loss. So as we heard before, remember the neural network, it passes through the input, through the weights and the function to provide an output. And then when it gets it wrong, when there's a loss, it backpropagates to improve its score. So the loss here in this graph on the left is minimizing the loss or getting better, right? So it's showing that the model gets more intelligent over time as you add compute and data, along with the number of parameters or weights and biases that are used. So these three things together show that essentially this formula works and it's scalable. So the more computing power and data leads to higher intelligence. And for the time being, this is a scaling law of intelligence that's worked. And this graph shows some examples of that. AlexNet here in the beginning is around the end of 2012. And you have various models that are mapped to this graph that show the increase in intelligence and compute. Gemini, GPT-4 follow along the same line. Now this I want to show you, this is just kind of for fun, but this little video shows that if you likened the volume of Lake Michigan to the capacity of our brain, because Lake Michigan has in fluid ounces about the same number of fluid ounces that would reflect the calculations per second that our brain would make. Does that make sense? So like our brain's capacity to calculate per second is equivalent to how many fluid ounces you would put into Lake Michigan. All right. So with that premise, if computing power doubles every 18 months, according to Moore's law, then how would it play out that we would fill this hole here with enough water to reflect the equivalent of the human brain's capacity to calculate? Let's see how that plays out. So we start off with it being barely perceptible that it's filling it all because it's every 18 months. And then if you notice there, right at the end, within the last 5 years, it fills up. And the reason for that is because it's doubling every 18 months. So it's kind of like compound interest. It builds up on itself so that right at the end, there's this geometric escalation of volume. And so in the same way, that's one of the reasons to explain why we're seeing such progression in intelligence and compute, because the doubling of compute time and also like the doubling of model sizes, which are related. So to recap, we talked about AI concepts and relationships at a high level. We talked about neural networks and deep learning and how does ChatGPT work, and then got a little hint of what this race to general intelligence is about. So I hope with that I've armed you with a beneath the surface, more than superficial understanding of AI and how it's working. And I really look forward to speaking with you more about this in class and hearing what your thoughts are. See you next time.